Welcome back to our statistics class notes, everybody. We're on page 105, which is the last page of section 7.3, and we're going to do another example here. And example 135. According to the NPR, National Public Radio, 52% of Americans owned stocks in 2016. So they're giving us a population parameter here, P, population proportion, equal to 0.52. Suppose a random sample of 200 Americans is taken. So we're going to do a sample of 200 Americans. We're trying to represent the population of all Americans. Would it be surprising to find that 45% of my sample own stocks? So the population proportion is 0.52. If I do a sample and in that sample of 200 people, I find that only 45% of that sample own stocks. P hat would be 0.45. I want to know if that would be surprising. So again, what I'm going to be looking at is a z-score, but I got to go through and make sure everything works first. So first I'm going to check the conditions needed to apply to satisfy the central limit theorem. Okay. I have to assume I have a random and independent sample. I have to make sure that my expected yeses, which in this case would be own stocks, would be at least 10 in my sample. Well, if I know the population proportion is 0.52, I multiply that times my sample size, 200. I would expect around 104 of my sample to say, yes, I own stocks. That's certainly more than 10. People that I would expect to not say, yes, I own stocks, in other words, to say I don't own any stocks, would be n times 1 minus p. 200 times 1 minus 0.52, which comes out to be 96. That's certainly more than 10. So the sample is large enough since we expect at least 10 successes, which means in this case own stocks, and 10 failures, in this case do not own stocks. And I can also assume that the American population is at least 10 times larger than the sample of 200, certainly, without question. So I can assume a normal distribution with a mean of p and the standard deviation of the standard error, which is the square root of p times 1 minus p over n. So 0.52 times 1 minus 0.52, which is 0.48, divided by n, 200. Take the square root, I get 0.0353. So the distribution of sample portions is approximately normal with a mean of p, the true population proportion p, 0.52, and a standard deviation of the standard error, which is 0.0353. So would a sample of 45% be unusual? Well, I have to plug it into my z-score. Okay, that's one way to do it rather than using the StatCrunch normal calculator and figuring out what's the probability that x is less than 0.45. We're just going to compute a z-score and see how far away 45% is from the mean. So that's going to be p hat, which is 0.45, minus p, 0.52, divided by the standard error, which is the standard deviation of 0.0353. And I get minus 1.98. So it's just on the border of almost being unusual, right? But it's not quite, because it's just less than 2, specifically 1.98. Standard error is below the mean. So it's not quite unusual, but it's pretty close to being unusual. As the last example here, in this section 7.3, according to the CDC, the percentage of adults who smoked cigarettes in 2016 was 15.5%. Okay, so they're telling you that the percentage of all adults who smoke cigarettes is 15.5%, which is 0.155 if I write it as a proportion. Suppose we take a random sample of 876 adults and find that 118 of them smoke. So in this case, I don't directly give you the sample proportion. You have to figure it out. You just take 118, divide it by 876. That'll be our sample proportion p hat, and that comes out to be 0.1347. Now, assuming that CDC figure is accurate, it's the population proportion, find the probability that if we were to take another random sample of 876 adults, the sample portion would be greater than or equal to this guy, 0.1347. So does the central limit theorem apply first and foremost? Yes, it's a random independent sample. It's a large sample. My expected number of yeses would be 15.5% of my 876, certainly more than 10. And my expected no's, I don't smoke, would be 1 minus that 15.5 or 0.155, or so that'd be 0.845. Times the sample size of 876 would also be certainly more than 10. 15.5% is more than 10, and so is 84.5%. So, and the third condition is that the population of adult smokers has to be at least 10 times my sample size, and I certainly think that I can know that there's more than 8,760 smokers in the U.S. All right. So that means the sampling distribution is approximately normal with a mean of 0.155, that's p, and the standard error, which we need to figure out. Standard error is p times 1 minus p divided by n, take the square root. So there's the calculation. It becomes 0.0122. Okay, so what I would have to do to figure out what's the probability of getting a value of 0.1347 or bigger is go to my StatCrunch normal calculator, put in the mean of 0.155 and the standard error of standard deviation of 0.0122. So if I do that really quick just to show you, I'm going to put in a mean here of 0.155. And my standard deviation was oh shoot, I just forgot, 122, right? 0122. Let me check that real quick. Yes, okay. So then I want to know what's the probability that x can be bigger than or equal to 0.1347. And I got it all in, I hit compute, and I get 0.95, etc., which is exactly what I see right here. And that's the end of section 7.3.